A symmetric matrix is not only diagonalizable, it is orthogonally diagonalizable. Okay, orthogonally diagonalizable. This means that there is an orthogonal matrix P such that P inverse AP is a diagonal matrix. An orthogonal matrix is a square matrix that satisfies P inverse equals P transpose. Okay, so a matrix is orthogonally diagonalizable if there is an orthogonal matrix P such that P inverse AP is a diagonal matrix. Now, the columns of an orthogonal matrix form an orthonormal set. Okay? The columns of an orthogonal matrix form an orthonormal set. Okay. Conversely, a square matrix whose columns form an orthonormal set is orthogonal. For example, this matrix this is an orthogonal matrix. Because its columns form an orthonormal set. Okay, so this column is orthogonal to this column, and each column has norm 1. We've said that a symmetric matrix is orthogonally diagonalizable. The converse is also true. If a square matrix is orthogonally diagonalizable, then it is symmetric. Let's return to our symmetric matrix A, given by this. We found that the set consisting of this vector forms a basis for the eigenspace of lambda equals 4. And the set consisting of these two vectors forms a basis for the eigenspace of lambda equals -2. The set of eigenvectors consisting of all of those forms a linearly independent set. Now, although this is good enough for diagonalization, it's not good enough for orthogonal diagonalization. For orthogonal diagonalization, we need a set of eigenvectors that are mutually orthogonal and have norm 1. Okay. The eigenvector 1, 1, 1 corresponding to lambda equals 4 is orthogonal to the eigenvectors given by this and this. Okay, so this eigenvector is orthogonal to the other two eigenvectors corresponding to lambda equals -2. Okay. For a symmetric matrix, two eigenvectors corresponding to distinct eigenvalues are orthogonal to each other. Okay, so since this eigenvector corresponds to lambda equals to 4, and these two eigenvectors correspond to -2, this eigenvector is orthogonal to this guy and that guy. Okay, note that this vector is not orthogonal to the other vector corresponding to the same eigenvalue. Okay. In order to get two eigenvectors in the eigenspace of lambda equals -2 that are orthogonal to each other, we can apply the Gram-Schmidt orthonormalization process to the basis for the eigenspace of lambda equals minus 2. Okay, so we can apply Gram-Schmidt to this basis for the eigenspace of lambda equals minus 2. Okay, so let's do that. Let v1 be 1, 1, 1, v2 be this vector, and v3 be this vector. Okay, we can just set aside v1. For now, we're going to apply Gram-Schmidt to v2 and v3. So let w2 be just v2. And let w3 be v3 minus the projection of v3 onto v2, or in this case w2. Okay, so that's equal to this vector minus v3 dotted with w2, so we get 1, and w2 dotted with itself, okay, that's 2, times the vector w2. Distribute that negative 1/2. And add these two vectors. Okay, good. Now normalize each of the vectors. Normalize each of the vectors v1, w2, and w3. Okay, so u1 is v1 divided by the norm of v1, and the norm of v1, if you look at v1 here, the norm of that is square root of 3. So we get this vector. Okay, u2 is equal to w2 divided by the norm. Okay, w2 is this vector here, so the norm of that is square root of 2. Okay, now U3 is W3 divided by the norm. Okay, look at W3 here. Take the norm of that. And you should get square root of 3/2. Simplify this. Okay, distribute that root 6 over 3. Okay, now I have U1, U2, and U3. They are mutually orthogonal and they each have norm 1. Form the matrix P with U1, U2, and U3 as its columns. Okay, so here's the first column. Second column. And the third column. Okay, P is an orthogonal matrix. P is orthogonal. And it orthogonally diagonalizes A. Let's check that P inverse AP equals this diagonal matrix. We know that P inverse is equal to P transpose because P is orthogonal. So P inverse AP is equal to this matrix times A times P. Okay, and if you multiply all of this out, you'll get this diagonal matrix.